you backpropagate, you assume all these weights are set in stone. And you only change the first few layers of weights. Then you get to say I did transfer learning. It's basically you're thinking, whatever the heck this network did in trying to make sense of dogs and cats, probably will also work for other images. Maybe you're wrong. But the only way I can figure this out is you do transfer learning, somebody else tries to basically train on all those images from scratch, and then gets better performance than you. One advantage of doing transfer learning is you don't need as many examples because you have much fewer weights to learn. Do you see what I'm saying? This is how actually medical research works, right? I mean, instead of just poking you guys, they poke on the monkeys, which are there somewhere in the university. After lots and lots of monkeys have been tortured, then they'll figure out something and they'll try to work on us. So human X-rays are few and far between. They're not that many. Cats, dogs, pictures, tons and tons of them. So you train yourself on cats and dogs, assume how can X-rays be different from cats and dogs? Very similar. Okay, take the first few layers, add a few extra layers, just change those weights. That's transfer learning. Okay, the last thing, since I got you up to here, I will just basically walk you through this. Let's see which one. No, I'll walk you just one slide and then you can go home. This is the engineering part. Essentially, that there are a bunch of fancy terms for basically you need to know what is the size of the filter. That's the kernel size. You need to know how do you move it. In the moving average, you need to move. The window has to be moved. If you move by 1 pixel, that's stride 1. If you move by 10 pixels, that's stride 10. This is all elementary arithmetic going under amazing AI. Okay? And then, so there is strides, there is, and then there is padding. Okay? So kernel size is how big is the convolutional kernel, the mask. The idea now is, at the time of actually the AlexNet, which started this whole convolutional neural networks being the state of the art, they were using 11 by 11 kernels. Now, basically the engineering understanding is the smaller the kernel, the better. And you put many kernels per layer, but smaller the kernel, the better. Okay? The next one is padding. This is just putting the zeros, just so that the image size won't change, so that image size only changes in one place, which is in the pooling layer. And the third is the number of filters. That is this man's problem. How many filters? Pick whatever the heck you want. Okay, remember you were going to get 625 weights before. Now you're going by with 9. I'm sure you can afford a couple more filters. Let's say 3 filters, 27 weights. That's not too bad. You see what I'm saying? You put more filters, etc. That's just basically an engineering decision. Okay? And then of course, you need to have a formula. It's been a long time since we had any formulas. You need a formula. And the formula is, if you have a W by W image, and an F by F kernel, and an S stride, that is the kernel is being moved S pixels at a time, and P pixels of zero padding around, using all your finite mathematics that you learned up until 7th grade or something, maybe 4th grade, you can show to yourself that the output size is O by O, where O is W minus F plus 2P by S plus 1. Looks like a fancy formula. But it involves division. So you should go back and tell your mom, another division today. Instead of depending on the slow rich uncle, I am doing my own stuff. Okay? And that's what basically this one is. Okay? So for AlexNet example, image size was 227 by 227, kernel size was 11, stride was 3, padding was 0, number of filters per layer was 96. Okay? So the output size basically for each of the output layers can be computed to be 55, and there would be 55 slices, one for each of the filters. One last thing which I won't go into slowly, but you should look at it, which is this computes the amount of memory taken, the number of parameters learned for each one of these places. In particular, if you're doing a f by f filter, you need f squared learned parameters. If you do k of them, you need k times f squared learned parameters. If you do a max pooling layer, you need 0 parameters. You need ReLU, 0 parameters. Then you do FC, it's m times m parameters. So if you look at this, for the AlexNet, the number of weights being learned, the total number of weights being learned actually are hugely dominated by the last layers. Every fully connected layer kills you. And all the other layers are much smaller in number. This is why people use parameter sharing. When you expect parameter sharing, you are expecting locality in the image, you are expecting structure in the image. This is exactly what logic does when it expects that there are relations between objects. There is structure in the world. If there is no structure, propositional logic is enough. If there is structure, you want to do predicate logic. Similarly, if there is no structure, fully connected networks are enough. If there is structure, you can exploit it by using this convnet idea, which is just really a specialization. Because everything convnet learns can be learned by fully connected network. Okay? Okay, this is one other thing that I should show you since I have this. You guys are last, so one more thing. So you can increase the amount of data, for example, if you are talking about images, for example, you want to increase the amount of data. Basically, if you can either get image, increase the data by just essentially taking pieces of the data. If a cat, as what's his name said, a rose by any name is rose. A cat by any cut is still a cat. Okay, or a cat by any slight occasion is still a cat. So if you think it is a cat, your system should be able to say it's a cat. So one cat picture can be made into 200 cat pictures. That's good job for you because you're increasing the number of layers. By the way, this is, if you go through this part tells you how to make the adversarial examples that I told you in the class. It's being written here. The same idea is being done for Deep Dream. The same idea, almost the same idea. Even in Deep Dream, you essentially keep the network weights the same and make the network see a few more things other than just the object that it has in front of it. And it turns out that for these networks, most convnets currently are trained on ImageNet database. ImageNet database has 1,000 classes. A full 200 of them are dogs. You understand what I'm saying? This is why I said when you go to sleep, you don't particularly dream of dogs, you dream of people, unless you're like a real doggy kind of a person. Convnet, because we have seen so many, most of our time we are spending time looking at people's faces, we dream of faces. We make up new faces. For convnets, it's so much easier to see dogs everywhere. By the way, this is for the people from India. Remember, you see any random thing and say, people from here see Mother Mary in the sliced bread. You toast it, suddenly, wow, there is a Mother Mary. Dogs will say, wow, there's a dog. It's what you want to see. And neural networks, basically, convnets trained on ImageNet can see dogs everywhere, which is why Deep Dream can get you pictures like that, dogs and cats, typically. Okay? Remember this, that we were able to do all of this because civilization advances by sort of ignoring small details and knowing confidently that it can be done. We have this slow but trustworthy gradient descent uncle who will take care of stuff if we just throw it to him. And then this last one, this is Lena, by the way. And she's a Swedish model. This was actually from a Playboy, and then they cut it off and they made this. And so at one point of time, CVPR, which is the annual conference for computer vision, they asked her to be the invited speaker. She came and she found, oh my God, each of you give me like a cent or something, 1 cent or something, because you use my picture. Mostly, this is the picture that you would see in the old image processing papers, right? And now, ImageNet, which is just an academic benchmark, is 14 million images. And Feifei Li obviously became very famous because she spent time making the first ImageNet. It's not technically challenging, but somebody has to sit down and make a benchmark. And she was able to do it because there are enough pictures already on the web. If she tried to do it in 1960s, she could have gotten 3 images. Lenna's sisters, Lenna's brother. That's it. So the last thing I want to tell you is, how many of you seen Blade Runner? So the original Blade Runner. Go back and see the original Blade Runner. Now, maybe this weekend. Okay? You would be amazed at how futuristic the movie was, right? We were always amazed. But now when you see it, try to see the little details that you missed the first time around. For example, Blade Runner basically thought TVs in 2049 will still be huge big bricks. And cell phones will be huge bigger bricks. They had air taxis. They could think of that. But they could think of TVs being essentially flat screen TVs. They could think of cell phones becoming smaller and smaller. The thing that happens in science is people who are working in a certain area try to think of what's going to happen in that particular area. The world at large expands in all directions. Much of what happened for this particular deep learning, really most of this technology was right there in 1980s. The thing that changed is every one of you got a cell phone and started taking pictures of your cats, and then dogs, then maybe your girlfriends, then maybe your boyfriends, and then the world is full of pictures. Point 1. Data is all over the place. So I think I mentioned this to you that it's not like United wasn't dragging people through the aisles before. Nobody was there to take a picture of it. It wasn't that white policemen were stopping African Americans for no good reason and giving them more tickets than they were giving to white men. Nobody was there to take pictures. Now everybody has a picture. I am very worried somebody is taking a picture of me saying all this stuff and it will be posted. Right? So that is the level at which the data capture has increased. Data was always being produced. We are capturing it. Did AI make data capture possible? No. It just happened because of the kindness of strangers. The same thing with GPUs. The compute infrastructure increased just by itself, not because we did anything. And it's useful to understand that while you are working in a certain area, sometimes hanging around and seeing what happens to the rest of the world might make your problem easier. Thank you. Let's have a good Halloween.